Hello, you are welcome to the mathematics tutorial for today. We are dealing with introduction to number bases. We want to learn about number-based systems, conversion from one base to another. So, if you have not done so, I want you to subscribe to the channel so that you can be notified when I upload new video. Remember the channel handle, youtube.com/@electro_teach. @electro_teach. Just subscribe to the channel. And as you watch this video, I want to also encourage you to like it and share and make your comments. I will personally respond to your comments. So let's go now to look at the lecture for today, the tutorial lecture for today, which is number-based systems. I want to look at number-based systems. Now, we all know numbers from 0, 1, 2, 3, 4, 5, and so on. Now, usually the number that we count from 0, 1, 2, 3, 4, and so on is in base 10. And if it is in base 10, we don't usually write the base. We normally omit writing the base system. Now, there are other base systems in numbers, such as base 2, base 3, base 4, base 16, and so on. Now, this base system can be converted one to the other. So, we need to acquaint ourselves with base system in engineering because it's very important, especially when dealing with digital systems. We usually have to work with bases other than base 10 that we usually use for numbers. More often than not, base 2 and base 16 are very much used than other bases. Now, let's look at, first of all, the base 10 system. Let's look at the base 10 system. We want to learn what base 10 is all about. Now, base 10 system is a system of numbering that all the figures used is from 0 to 9. 0 to 9. So because it's in base 10, when you reach 9, then the next one will go back to 0, 1, 2, 3, and so on again. So let's look at this example. We have the example of this number, 4235.325. This is a number and it has decimal numbers also. Like I said, we want to know that the addition, subtraction, multiplication, division that we have on the screen here, they are actually performed in base 10. They are performed in base 10. Now, the number up here has something that we call place values. Place values. The place value of each of them are in power of 10. Let me break that down for you now. Let me work it on the screen so that you can see what I mean. This is equal to all the numbers here multiplied by the powers of 10 added together. For instance, we can express it this way. 4 multiplied by 10 raised to power. All of them we have powers. Now, the powers that we have, the powers of 10 on them accordingly. This one we have power to the negative 3. The 2 here, we have power to the negative 2. That is to say, the base 10, the base, we have power to negative 2. That is minus 2. Minus 2. And this one will be minus . minus 1. Now, the whole number that are not the decimal, we have power from 0, 1, 2, 3. So we count from the power, the last digit. Last digit has power of 0. The base 10 has power of 0. Next one power of 1. Next one power of 2. The next power of 3. So what we have here, it can be expressed this way. 4 times once we show the power here, okay. The base raised to power 3 plus 2. This is the first one, 4. The next one is 2. 2 times the base, 10 raised to power of 2. Raised to power of 2. The next one is plus 3 multiplied by the base raised to power of 1. The base is 10 raised to power of 1. Then plus again 5 multiplied by the base again raised to power of 0. The base is 10 to the power of 0. Now what we have here shows the place value of the numbers here, the digits. The base has a place value of 0, 1, 2, 3, going backward like that. Now, the decimal numbers, they have the place value accordingly, as I've shown here. So you can now add that one to the whole number plus 3 multiplied by the base raised to power the number there. We have 10 to the power of 10 to the power of minus 1 plus 2 multiplied by the base again raised to power minus 2 minus 2 plus 4 times base again raised to power of minus 3. So that's what you have. So if you do the summation of all of these, you are going back to get the answer that we started with. That is 4235.324. This is the breakdown of the number in its base 10 system. We have broken it down in its base 10 system. So you can see how they carry the place value, each of them. Now, the same can be done for other base systems. We can express the numbers in other base systems in similar manner. And of course, this is what we use to convert from one base system to another. That's what we use to convert. All right, so let's proceed to see the number bases one by one. We want to look at base 2 number system. Base 2 is called binary. And then when you are dealing with base 2, you will realize that all the digits you are going to use, there will be no 2 among them. Rather, you are going to have numbers below 2. That is 0 and 1. There cannot be 2, 3, or 4. Any base you are dealing with, the numbers you use to express, the digits you use to express your number will be less than, all of them will be less than the base that you are dealing with. So as we are dealing with base 2, which is the binary system, we'll be using 0 and 1 only. There will be no 2, 3, 4, because the base is base 2. All of them will be less than the digit 2, the figure 2. All right. Now, look at examples of numbers expressed in base 2. These are various numbers: 1010, 1100, 1001, 1111, 10.01, 11.10. You will realize that when I call these numbers, I did not call them as 1010, 1100, 1001. No, they are not that. If you call 1000, you are dealing with base 10. Here, we are dealing with base 2. So you call them one digit at a time. 1, 0, 1, 0, like that. 0, 0, 1, 1, 1, 0, 1. You do not call it as a whole number as in base 10. You call them one digit at a time. Now, let's look at the logic of place values now to analyze the binary number. So the binary number we have here, for instance, is 111.11011. Now, this number can be converted to another base like base 10 or base 16. As it is now, we don't know the number that it is in base 10 unless we carry out the conversion. Or that is typically the base system, base 2 numbering system. You see that all the figures, all the digits you use, they are only 0 and 1 because we are dealing with base 2. Now, in engineering, another popular base system that we use is the base 16 system. Base 16 is termed hexadecimal. Hexadecimal. Now, when you are dealing with base 16, there's a special way by which base 16 is represented. You use numbers to represent base 16 as well as letters A, B, C, D, E, F, and so on. Now, the numbers that are used in base 16 include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, you see that all these numbers are written 1, 1, 1, 1. There are no 2 numbers written together. When you are about to get to that stage, that is when you get to 9. As you are moving on to get to 10, then the numbers are represented with alphabets. The numbers are represented with alphabets. So A, B, C, D, E, F represent numbers in the hexadecimal system. For instance, A represents 10. B represents 11. Then C represents 12. D represents 13. And E represents 14. Then F represents 15. So this is a base 16 system. Now remember, the base you are dealing with is base 16. All the numbers will be less than 16. So you will have 0 to 15. So we are going to stop at A, B, C, D, E, F. Since 15 is the highest one that we can get, that is less than 16. So we will not write 16 to be represented since we are dealing with base 16. Anything 16 and above cannot appear in base 16. So this is a representation of the hexadecimal base system, which is a base 16. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That is a hexadecimal representation. Let's look at another one, which is a base 8. Base 8 number system is the octa. Octa. Now, any numbers expressed in base 8 will be from 0 to 7. We cannot have 8 and above because we are dealing with base 8. All the numbers we are using will be less than 8 to include 0 to 7. So you can have numbers written like this on the screen that you are seeing here: 423.7, 777.4, 207.702. You cannot have something 8 point something or something 0.89. No, the highest you can have is 7. And so you can have it such that you know that you express it in base 8. All right. Now we have looked at the common base systems that we use. We don't have to talk about base 3, base 4, base 5, and the rest. The principle that we have applied in base 2, base 8, and 16 is sufficient to deal with other base systems within that. Now, to convert from one base to the other, we need to look at what we have on the screen here. That is conversion from one base to base 10, from other bases to base 10. To convert from other bases to base 10, we use a straightforward method, which is the same thing to in other bases. Look at it, for instance. The method runs through other base system when you are converting them to base 10. So we want to have examples of the numbers on the screen. We want to convert them to base 10. These numbers are in base 8, base 2, base 16, and base 2 again. So let's see. We are converting all of them to base 10. The solution is here. For instance, the first one is 442 in base 8. 442 are in base 8. So we are going to use the place values of numbers to convert them. We have 442 base 8 equals, remember we are dealing with base 8. So the 8 will be having powers from here: 0, 1, 2, that is going backward. So the 8 will be having such power. Then we add them all up when we multiply by each number on the digits. So the first one here, 4. Since we are numbering from here, 0, 1, 2, the power of the base system on these digits is actually 2. So we have 4 multiplied by the base raised to the power of 2. And that's what you have here. 4 multiplied by 8 raised to the power of 2. Likewise, the second one added will be 4 multiplied by the base raised to the power of 1. This is power 1 and this one is power 0. So we have 2 multiplied by the base raised to the power 0 for the last one. Now, when you do that and add them up together, you have what we have here: 4 times 64 plus 4 times 8 plus 2 times 1. Now, when you add them up like this, you get 256 plus 32 plus 2. That is 290 in base 10. So you've converted 442 in base 8 to 290 in base 10. That's very simple and straightforward. So the same method will be employed to other conversions in the example. Now we have the second one, 1110.111 base 2. Just like the example I did up earlier, you can convert this number in base 2 to base 10. Now we are in base 2, so the base will be having powers. Each digit here has a place value. The place value of this first one here is 3. The next one is 2. This one is 1. And the 0 here is 0. And for the ones that are decimal points, the first one is a -1. Second one is -2. That's the second one here. And the last one here, the one that I written last year, is a -3. So we add them up by adding the digits multiplied by the base taken to the power of the place value. 1 times 2 raised to the power 3 plus 1 times 2 raised to the power 2 plus 1 times 2 raised to the power 1 plus 0 times 2 raised to the power 0 plus 1 times 2 raised to the power -1 plus 1 times 2 raised to the power -2 plus 1 times 2 raised to the power -3. So when you do that, you can have the breakdown of the figures here as we have. 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1 plus 1 times 1 over 2 plus 1 times 1 over 4. This is 1 over 2, this is 1 over 4, and this is 1 over 8. So plus 1 times 1 over 8. Now, if you add all of them up, we have what we have on the screen, which is 14.875 in base 10. 14.875 in base 10. Now, base 2. Base 2 was 1110.111 base 2. Now, base 10 is 14.875, which is equivalent to 14 whole number 7 over 8. Now, the next one is in base 16. We have a letter there in the question. Number 3, 2D3.A16. 2D3.A16. So let's follow the same pattern. This will be 2 raised to power 2. The place value will be raised to power 2. 2 times 16 raised to power 2 plus D times 16 raised to power 1 plus 3 times 16 raised to power 0 plus 8 times 16 raised to power minus 1. Now, remember, your D is represented as a figure, which is 13. Your A represented as a figure, which is 10. So if you substitute for those values, we have this written out. 512 plus 13 times 16 plus 3 plus 10 over 16. Now, when you multiply all these out and then add them together, we arrive at 723.625 or 723.5 over 8. And that is what we have. That is the decimal value of 2D3.A16. Now, let's look at the next, which is the last example. It's also in base 2. 10010 in base 2. Converted to base 10, we follow the same pattern. We have this. We have this. The first digit here is taken to the power of 4. The place value is 4. The place value of this is 3. And this is 2. And this one is 1. And this one is 0. So, without doing much, we know that you multiply all these 0 by anything, you get 0. And so these 2 will actually give us 0. This 0, 0 will give us 0. But this 1, 1 will give us number. Even the last one, 0 multiplied by something, will give us 0. But the first digit here and the fourth digit will give us numbers. And those are the ones that we can handle now. 1 times 2 raised to power 4 plus 1 times 2 raised to power 1. And that's simple and straightforward. In this also 1 times 16, plus 1 times 2. That is 18 base 10. 18 base 10. The base is now base 10. But usually when the number is expressed in base 10, we don't normally write the base system. So you can actually delete the base system and write the answer only as a base as base 10 without putting any other number, without putting the base. Now, how do we convert from base 10 to other bases? To convert from base 10 to other bases, what we do is a long division. You carry out a long division, then we'll be taking note of the remainders as you are carrying out the division. For example, we want to convert this number here, 55 to base 2, 55.55 to base 8, and 12.57 to base 16. So the first one, 55 to base 2. We have a long division. 55 here, we are using 2 to divide it. The base is what you use to divide the number. So if you use 2 to divide 55, your answer will be 27. But since 55 is an odd number, you have a remainder after the division, and the remainder is 1. So you write the remainder in front here. This is the remainder. Now, you go ahead again, use 2 to divide 27, you get 13. And the answer is also 13 remainder 1. If you use 2 to divide 13, you get 6. And the remainder is also 1. If you use 2 to divide 6, you get 3. And the remainder is 0. Okay, the remainder there is 0. That means you have come to the end of that. You have come to the end. So you can now go ahead. There will be, the next one will be 2 divided by 3, and the answer will be 1. and the remainder will be also 1. So here we can actually delete this unnecessary row. It's causing a confusion here. So this is how it is. This is how it is. So 2 in 3, 3 divided by 2, we get 1, remainder is 1. Then this last one, you now use 2 again to divide it. So 1 divided by 2, you cannot get 2 out of 1, so that's the answer will be 0. So you carry that remainder, the 1 itself, as the remainder, and write it as the last remainder. So you now read the answers from bottom to top. You look at this arrow. This arrow is showing the direction of reading the remainders. So the remainders are the answers to the problem. 55 base 10 converted to base 2. So the answers will be 1, 1, 0, 1, 1, 1. And that is a solution to the first one. The second one is a number that is having decimal points, decimal digits, and then we want to convert it to base 8. We want to convert that number that has decimal digits to base 8. So let us see. All right, so 55.55 is equal to 55 plus 0.55. Now the 55 can be handled by doing a long division, 55 divided by 8 as a long division, and we write down the remainders. So first, 55 divided by 8, the answer will be 6, and the remainder will be 7 here, because 8 times 6 is 48. So the remainder will be 7. Then again, we say 8, we use it to divide the remainder here, the answer here, which is 6. 6 divided by 8, the answer will be 0, and the remainder is now 6. We carry the 6 itself out as the remainder. Now, we have taken the division of the whole number parts, and the answer will be read from bottom to top. Look at the arrow again, going from down to up. So the answer will be 6, 7. Now, what about the decimal portion of this number, 0.55? We want to do the division of that also. Now, 0.55, we are going to convert it to base 8 in this manner. 0.55 multiplied by 8, So for the decimal part, we carry out a special multiplication, as you can see on the screen. So 0.55 multiplied by 8, that is the base. We have 4.4. The whole number is carried out here as the remainder. And then what is the answer? The remaining part is left as 0.4. Now that 0.4 again, you go ahead and multiply it by 8, you get 3.2. You take the whole number part out as the remainder, and then you retain the 0.2 inside. You go ahead again, 8 multiplied by 0.2, you get 1.6. Take out the whole number parts and retain the remaining one as the remainder. Now go ahead again, 8 times 0.6, you get a 4.8. You take the 4 parts, the whole number out, and retain the remaining one, 0.8 as remainder. You go ahead again and do a multiplication, 8 times 0.8 again. 8 times 0.8, we have something 6.4. You take out the whole number 6 outside and retain the 0.4. But with this long multiplication, you read the answers out from top to bottom, since the number we are dealing with is actually a fraction. It's a decimal fraction. It's not a whole number. So we'll read it out from up, 4, 3, 1, 4, 6. So we can write the answer together now with the answer to the whole number long division that we carried out, which was actually 6, 7. So the answer will be 67.43146 in base 8. That is 55.55 in base 10 converted to base 8. Now we move on and do conversion of a 12.57 to base 16. That is in base 10 to base 16. 12.57, we carry it out in a similar manner. The whole number parts and the decimal will be handled separately. So we are going from base 10 to base 16. So what do is we divide first the first parts, that is whole number, with the base 16. So 12 divided by 16. You can see that we cannot get 16 out of 12. So the answer will be 0. Remainder is 12. And that 12 is represented as C, not as figure 12. Not as figure 12. So we write C out. Then the decimal parts, we'll do a long multiplication to get the answer to that in base 16. 4.56 times 16, to get something like 9.12 rather. Then you take the whole number out, retain the decimal inside. Then you go ahead again, 16 times 0.12, you get something like 1.92. You take the whole number out and retain the fractional parts. So you go ahead like this. Next one will be 0.92 times 16. That gives us a something like a 15.72. And that's a whole number. 15 is represented as E. 14 is represented as E. So likewise, so 0.92 times 16 is giving us 14.72. That 14 whole number will be taken out, but we are not going to write it as 14 under base 16, but we use the letter to represent it. So the letter is E. Now we go ahead again, 0.72 times 16, that gives us around 11.52. That 11 is represented as B, we will not write 11. So we write B and retain the decimal inside. Continue again, we multiply the decimal by 16. Then we get 16 times 0.52, that gives us about 8.32. So we bring the whole number out and retain the decimal inside. Now, after carrying out this, we read the numbers, the remainders, from top to bottom, 91EB8. So that will be added to C that we have obtained up here. So the answer will be written together as C.91EB8. And that's the final answer, C.91BE8 in base 16. That is conversion of 12.57 in base 10 to base 16. The answer is C.91EB8 in base 16. All right. Now, in digital system, we use certain terminologies that are related to the base system, the binary system, which often use digits 1 and 0. So we want to be familiar with these terminologies in digital systems. For instance, we talk about logic. When we talk about logic, we talk about binary digits, logic 0, logic 1. Then we also talk about bytes. We also talk about bits. The three items here, 1, 2, 3. The first one is bits, which is actually either a 0 or 1, which is actually a digit in binary system. It will either be 0 or 1. That's a bit. Now, bytes is 8 group of bits. When we have 8 group of bits together, we have a byte. For instance, let's look at this number in binary system, 1101101. That is a byte in a binary system, in digital system. And also, nibble means 4 binary digits, 4. Instead of 8 that we call bytes, then we can have a nibble, which is half of a byte. Like, for example, we have 1111 or 1101. These are examples of nibble. Now, we want to look again at a direct conversion from base 2 to base 16. How can we do that? We want to convert a base 2 to base 16 directly instead of going to base 10 first. So we have examples here that will help us to do that. Now, 3 examples. First one is 11111 in base 2. Then we want to convert it to base 16. We now have 0001, 1111. And the same, this gives us the answer to that. This is 1F in hexadecimal, 1F. Now, why do we have 1F? Because we can group this number into eight bit system. If you group it into 8-bit system, we can add 3 zeros before this number to have 0001, then 1111, everything in base 2. All right. So the first one here is a 0001, that is this one, and 1111 is F in a hexadecimal. The second one is 11010. If you write it in a group of 4 in nibbles, you can have 0001, 0001, then 1010. And this is 1A in hexadecimal. Remember, A in hexadecimal is 10. That's 10. And F is 15. Okay. So the same thing applicable to this one. We group it into 444. We have something like 0010, 1010, then 1011. And then this gives us 2AB. This is 2, this is A, and this is B in hexadecimal. The next one is addition, subtraction, multiplication, and division of number systems. We can multiply, can add, we can subtract our numbers in number system. We can also carry out division. But remember, when we carry out this division, multiplication, and addition, it has to be in an equivalent base system. It has to be taken in their base system. We cannot just do it in base 10. The answer must be in the base system of interest. So we have the examples here to help us understand this. 1111 in base 2 plus 1010 in base 2 minus 1001 in base 2. So we want to know that. So if you want to proceed, you must bear in mind that there's a preference that we carry out operations in mathematics, and that preference is actually called board mass. So brackets of division, multiplication, addition, and subtraction. So the one that comes first is what we are going to carry out first. Here, addition is coming before subtraction. So we need to add these two first, add them together in base 2 before we go ahead and then subtract the last one from them. So to add them in base 2, this is what we have. 1111 plus 1010. We want to take examples on the addition and subtraction of number-based systems. Let's look at the screen now and see the examples of addition, subtraction, multiplication of number systems. The first example is the addition of 1111 base 2 to 1010 base 2 minus 1001 base 2. Now in this system, we need to use board mass to do the addition. We need to follow the principle of arithmetic and addition, multiplication, and division. So we follow board mass as we see on the screen, brackets of division, multiplication, addition, and subtraction. So here, the first one we are going to take will be the addition. Then we do the subtraction from the result of that. So adding this together, we have 1111, 1010. 1 plus 0 will be 1. 1 plus 1 will be 2. But since it's in base 2, you take 2 out of it. How many times will you get 2? 1 time. So the remainder is 0. So we write the remainder down here. Then the one that we got out, we add it to this other one up here to make it 2. So how many making 2? How many 2 will you get from 2 again? It is 1, remainder 0. So we put 0 down and take that one to the next column. So if you add it, 1 plus 1 plus 1 making 3. Now we take 2 out of 3. How many times you get 2? Get it 1 time. Remainder is 1. So write the remainder down and carry the one that you got to the outside here. So we now have the addition of that as 11001. Now I want to subtract 1001 out of that. So the two of them are in base 2. So we go ahead to do the subtraction. 1 minus 1, 0. 0 minus 0, 0. 0 minus 0, 0, 1 minus 1, 0, 1 minus 0, 1. And the answer is 1, 0, 0, 0, 0 in base 2. So the final answer is of the addition and subtraction of 1, 1, 1, 1 plus 1, 0, 1, 0 minus 1, 0, 0, 1 is 1, 0, 0, 0, 0 in base 2. Now we're moving on to the second example, which is the multiplication of numbers in base 8, 555 base 8 times 14 base 8. So we can write it as normal multiplication like this, 555 times 14. Now as we multiply, we will add the results of each multiplication up. But since it's in base 8, anytime we are getting a number from 8 and above, it is the remainder that you'll be writing down. We will not write anything higher, up to 8 and above. For instance, if you multiply the first set, 4 multiplied by 555, we get 2664 as written down here. And the second one, 555 multiplied by 1, we get 555 like this. Then when we are adding them together, 4 plus 0, 4. 6 plus 5 is 11. But since it's in base 8, we take 8 out. We can get 8 one time, and the remainder will be 3. That 1 will be taken to the next column. But we write the remainder 3. 1 plus 6 plus 5 is 12. Now we take 8 out. Since it's in base 8, the 8 taken out will give us remainder of 4. And then we can get 8 one time. We take that 1 to the next column. 1 plus 2 plus 5. That is 8. We take 8 out. We get it one time, and the remainder is 0. We write 0 and carry the 1 to the next column. The answer to that, 555 base 8 times 14 base 8 is 10434 in base 8. The answer is in base 8. So the answer should be written as this. One 10434 in base 8. In base 8. That's the final answer to that. The next one is number 3. We are having a division of numbers in base 2. 1, 1, 1, 1, 0, 0, 0. 1, 1, 1, 1, 1, 0, base 2. So what we are doing is division of 1, 1, 1, 1, 1, 0, 0, 0 divided by 1, 1, 1, 1, 1, 0 in base 2. So we do a long division. This is the factor here, and this is the number that we are using as to divide, the number we want to divide. So what we do is 1, 1, 1, 1. How many times we get it from here? We get it we get it one time. Write 1 down. Okay. Then if you multiply it, you write it out here. Then when you write it out, you now subtract that, you get this 0, 0, 0, 0, and take this remainder, and you say this one to divide it again, you get it 0 times. Okay. Okay, you get it first time there was 1 remainder. Now there is no remainder. 0, 0, 0, no remainder. Write it 0. Then lastly, you divide it again. You get 0 again without any remainder. So the answer will be read out from here: 1, 0, 0 in base 2. 1, 0, 0 in base 2. Okay. Now, this long division of binary numbers is kind of cumbersome and difficult to understand. That's understandable. So what you do in this case is to use base 10 to do the work. So first of all, you convert the 2 numbers to base 10. You convert the quotient and divisor into base 10. Convert this number to base 10. Convert the second number to base 10. Then you carry out the division. After carrying out the division, whatever you get, then you convert it back to base 2. You will discover that the answer will still be 100 base 2. 100 base 2. So you try out at your own convenience and check the answer. All right. Now let's look at the next example. If 23 base x is 1111 base 2, determine the value of x. So the question wants us to know which base was this 23 that was equivalent to 1111 base 2. So the solution, what we do here is to convert both sides to base 10. We convert both sides to base 10. 23 base x, 23 base x equals 111 base 2. So you convert this side to base 10, you convert the other side to base 10 and equate the two of them together. And this is a process using their place value. So you could see the process here. 2 times x raised to power 1 plus 3 times x raised to power 0 equals 1 times 2 raised to power 3 plus 1 times 2 raised to power 2 plus 1 times 2 raised to power 1 plus 1 times 2 raised to power 0. Now, when you express it this way, you can take this one and determine their value. The value is 2x plus 3 equals 8 plus 4 plus 2 plus 1. And then you can simplify that to get 2x is equal to 15 minus 3. That is 2x is equal to 12. Therefore, x is equal to 6. X is equal to 6. So that is it. So the base of the original number 23 is in base 6. This is in base 6. So that is it. So that is how we came to the conclusion. Now, as a review, hexadecimal, remember the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 are used with the letters A, B, C, D, E, F. Whereas A, B, C, D, E, F represents 10, 11, 12, 13, 14, and 15. So that is what we use. In hexadecimal, we use the letters to represent those numbers. Okay. And then when you want to convert a decimal to hexadecimal, what do? You do long division. You use base 16 to divide the number. Then you write out the remainders. The remainders will be the answers. But mark you, the remainders, as you know, from 10 to 15 will be represented by letters A, B, C to F. A, B, C to F. So we have a simple example here that was carried out once again to, refreshing our memory. The question is to divide 42, to convert 42 in base 10 to base 16. So we use 16 to divide it. Remainder first is 10. The second remainder is 2. And that 10 will be represented as A, and the second remainder is 2. Now, when we do that, we can now write it as 42 base 10 is equal to 2A in base 16. Now, if you are going from hexadecimal to decimal, that's going back, then we can use the place value representation that we normally do. That's an example that we have here. Then you can practice this other problem that we have here on your own. You can convert 162 in base 10 to base 16. That's a practice problem that you can actually try. 162 in base 10 to base 16. So that's how we come to the conclusion of the tutorial on this number-based system. So I want to encourage you to go through it again and practice the problem there and confirm that the answers we obtained are right. Now, if you have not done so, don't forget, like this video, share it, and you can actually, you need to actually subscribe to the channel if you have not done so. Subscribe so that when next I'm posting a new video or for tutorial lectures like this, you will be notified. Thank you very much for joining the class. Till next time.